You know, but as we, you know, as we near lunch, if you want to get up and leave, just try to do it quietly and respectfully. We'll be all set. So,
cool.
Take it away.
Thanks a lot, Ron. Thank you, everyone. Is the mic getting me? Is it good? Can you hear me? Okay. Barely? All right. Is that any better? Yeah? Okay. So, those of you who saw me last night know that I had no voice whatsoever. So now I have partial voice. Yay. Partial voice. I get a little excited sometimes when I talk about SDR and when I talk to a big room full of people who are excited about SDR for 4 days straight. Sometimes I lose my voice, apparently. So I want to talk about spectrum monitoring with software-defined radio. Hopefully everybody has a basic idea. Have you heard of software-defined radio before? You have something? I know. Okay, right. So it's just the application of digital signal processing to radio. So I like to tell people who are new to software-defined radio that it's like a sound card for radio. Right? Like your sound card can record arbitrary sounds, produce arbitrary sounds, replay, whatever. Same kind of thing, but with radio waves instead of sound waves. And we have all these wonderful, wonderful tools now for software-defined radio. I got this Realtek dongle here and HackRF and all kinds of stuff. But when people are new to software-defined radio, one of the things that they are probably very likely to see right off the bat is something like this, a waterfall plot. And a waterfall plot is a moving spectrogram. And a spectrogram gives you time on one axis and frequency on another axis. And then the relative power level is indicated by a color of a pixel. So it's super informative. If you haven't ever seen anything like this and you see it for the first time, it's like, wow, amazing. There's so much information there. It's incredible and eye-opening, and you can see a whole bunch of different signals. So like in this case, this is actually a video that I pulled off of YouTube. That was somebody using HackRF to tune into, I think, some cellular bands in Europe. And you can see a whole bunch of different channels in use, and a single channel ends up as a vertical line or a vertical row of little blips or something in the moving spectrogram. And it's so cool. It contains so much information. But over time, if you use these things, you might notice that, well, it's cool, but it has some limitations too. This is another example of a similar sort of display. The SDR world is full of different software implementations that all use this popular kind of waterfall display. So here's one called RF Analyzer for Android. And you can just plug in your tablet or your phone right into a HackRF or a Realtek dongle and get a waterfall display right there. It's really handy. Another one is the PortaPack for HackRF that Jared Boone here designed. He was my co-designer on HackRF1, and now he's producing this add-on for HackRF1. So this is like the regular HackRF1, but then if you put his PortaPack on it, oh, gotta grab the battery. Thank you, Mike. So you have a little, nice aluminum case and a front end board that has an LCD on it. And so what do people want to do with the PortaPack? Of course, they want to look at a waterfall display, right? Everybody wants to look at a waterfall display. It does other things too. It can do like decoding and audio and stuff. It's a cool toy, handheld SDR platform. But probably the main thing that most of the people are going to do most of the time with PortaPack is the same thing they do with every other SDR platform, and that's stare at waterfall displays. These waterfall displays are super awesome, but they have some problems, in my opinion, or at least maybe problems isn't the right word, but limitations. They have some limitations. One of them is that transient events can be completely missing. And this is something that throws people for a loop sometimes, I think. It looks like you have such a complete picture of what's going on. But I want you to think about this with me. Do a little math in your head. A HackRF, for example, is capturing 20 million samples per second. It's measuring the signal on the antenna 20 million times per second. Okay, 20 million. It's a big number. Okay. How many horizontal rows are in this LCD display, or are in the display of any display on which you're watching a waterfall plot? 320. Jared knows the answer exactly, of course. Generally speaking, you're going to be looking at a waterfall plot that has maybe, a few hundred lines at the most. Each line has, or let's say, how about this? How many rows appear per second? I don't know, 30-ish? Something like that? I don't know, tens of rows at the most? So you get, okay, let's give them the benefit of the doubt and think we're getting a lot of information here. Let's say you get 100 rows in 1 second. Okay, you're getting 100 rows in 1 second, but we measured, and each row probably was computed over a few hundred, or maybe, let's say, 1,000 samples. So 100,000 samples are getting, this is like best case, 100,000 measurements are getting displayed on the screen in 1 second. But there were 20 million measurements made in that second. You're only seeing 100,000 out of 20 million. And in most cases, that's probably the best case scenario. Roughly speaking, you're probably missing hundreds to maybe 1,000 times the information compared to what you're actually seeing on screen. Where does all that missing information go? Well, it gets lost between the horizontal rows of your waterfall display. You see a row, and then some time elapses. Maybe it's only, a tiny fraction of a second. But then you see another row, and in between those two horizontal rows in your waterfall display, or those two time rows, you completely miss things that can happen. Now, you might think, well, you'd only miss very short things, but guess what? Radio technology these days is full of very short things. Do you know how long a typical Bluetooth packet lasts? It lasts about 200 microseconds, maybe 500 microseconds. Microseconds, not milliseconds, microseconds. So, and that's just one example. Our daily lives are full of more and more interesting digital wireless technologies that use super, super short packets of information. And you can completely fail to observe them even if they're right in the middle of what should be in your waterfall display, because you didn't happen to get lucky enough for one of them to happen at the right time, so you get a little tiny blip in one horizontal row of your waterfall. Wow. So transient events are very difficult to observe with this type of display. Another limitation of waterfall displays is that you can only see a certain limited period of time. Now, you can turn down the speed of the waterfall, in which case the other problem becomes more severe. But these are two sort of, you have a trade-off there. The faster your waterfall, the less time you see. And sometimes it's nice to observe trends over time. If you're only looking at a few seconds of information at a time, you can't really observe trends very well. Another limitation of waterfalls is that you get limited bandwidth. Now, HackRF, for example, operates over about 6 gigahertz of operating frequency range. But the instantaneous bandwidth that it measures is only 20 megahertz. So you see in the waterfall, at the most, about 20 megahertz out of 6 billion hertz, 6 gigahertz. You're seeing a tiny fraction of its tuning range, which can be nice. 20 megahertz is a lot for many purposes, but wouldn't it be nice to use the hardware a little bit more effectively to survey much more bandwidth? And spectrum surveying or spectrum monitoring is something that is an important use of software-defined radio technology, I think. It's something that is extremely useful for observing how we use spectrum, measuring how we use spectrum, checking up to see how good our spectrum management is. Like, are we utilizing this public resource effectively and sharing it effectively? Are people abusing the spectrum? And can we fix that? How do we find and fix those problems? Wide spectrum monitoring is useful for all sorts of things. It's useful for radio astronomy. It's useful for just all sorts of different applications. And what we find is that there aren't a lot of tools, or there haven't been a lot of tools until recently, to do that kind of spectrum monitoring without using like high-end equipment, very expensive equipment, not lower-cost equipment like these. So the first thing I want to show you that I'm sure some of you have seen before is a wonderful piece of software called GR-Phosphor, phosphor with an F, a GPU accelerated waterfall display. This is something you can use to solve one of those three limitations. And that limitation is the problem observing transient events. This is some open source software from TNT in the Ossmann group, and check this out. Okay, slightly faster, or a lot faster. And not only is the waterfall display super fast, not only is it moving super fast, but also look at the kind of heat map spectrum display at the top. If you look at like the little red line over the top of things, you can actually see things show up that were so transient that you might not have been able to see them at all. And so it's sort of a guide for your eye that shows you like the probability of events, or the duty cycle of events, like things that happen super fast that you would never see with your eye on this kind of display actually get indicated as something that appears and then disappears. It's amazing at capturing transient events. And the reason it's able to do this is because it's GPU accelerated, and just because the author of the software decided to, he set out to solve this problem of not being able to see transient events. It's just a better waterfall than most waterfall displays. Now, for certain purposes, though, it might not be better, like the limited time displayed problem. Right? We're seeing even less time displayed on a waterfall now when we use phosphor. But if your concern is to see transient events, phosphor is amazing. And GR-Phosphor is a very similar display to something you might have seen before on real-time spectrum analyzers. If you've ever bought a spectrum analyzer, a piece of RF test equipment, first of all, you spend a lot of money, probably, and second of all, you probably bought a traditional or swept spectrum analyzer, unless you really spent a lot of money, and you got a real-time analyzer. And these things start somewhere in the tens of thousands of dollars. And a real-time spectrum analyzer does exactly what GR-Phosphor does. It tries to show you everything that happened during a limited window of time and frequency. And if you look under the hood of a real-time spectrum analyzer, you'll find something very similar to this. It is simply a high-end SDR platform with software on the front of it that is similar to GR-Phosphor. So how about the limited time display? How do we observe spectrum over a longer period of time? Traditionally, when people start to solve these problems, like observing spectrum over a longer period of time, or observing spectrum over much wider bandwidth, they turn to a spectrum analyzer. And this is the cheapest spectrum analyzer I could find that has as much bandwidth, operating frequency range, I should say, as a HackRF. And it is, I think, $8,000, something like that. So it's a big jump in cost to go to some of these more traditional solutions for spectrum monitoring. But here's how they work. Assuming that you're using a swept spectrum analyzer or the lower cost type of spectrum analyzers, like this one, as opposed to the real-time spectrum analyzers, it works like this. Over time, it tunes a radio receiver. It sweeps the frequency. And so the red line here in this plot shows you how the frequency is increased over time, and then it jumps back to the beginning and it's increased over time. And then it jumps back to the beginning and it's increased over time. It's only really measuring the radio energy at one frequency at one time. It's not actually measuring all frequencies all the time, which is something I'm not even sure a lot of first-time users of spectrum analyzers realize, that those things have limitations too. Again, these kinds of devices can have problems picking up transient events, because if an event at a particular frequency happens between two sweeps, it just misses it completely. But they're super good at sweeping over a very wide range of frequencies. Really good at that. And that's one of the best reasons to use a traditional spectrum analyzer. And you can also often configure these things to give you data over a longer period of time in some way. So they're good for those things, and they have a nice, front end and everything. But sweeping with these smooth analog curves or lines is not the only way. You can also sweep in steps or do digital sweeping. You can measure a range of frequencies, usually a pretty narrow range, and then step to the next range of frequencies, and then step to the next range, and then step to the next. And effectively, you get the same type of measurement if you're looking over a wide bandwidth. And this is a very easy sort of thing to implement on, for example, low-cost digital radio transceivers, like the IME, my favorite pink toy, and now everyone's favorite pink toy since Sammy. The IME, I was introduced to by Travis Goodspeed, and he taught me how to program it, and then I said, hey, I could build a spectrum analyzer out of this. So I wrote software to be a spectrum analyzer, and what it does is it tunes its little radio chip to one frequency, takes a measurement of the radio energy, and then plots one pixel to the screen, or one column of pixels to the screen. Then it shifts over to the next frequency, and it tunes the radio, it takes a measurement of the energy, and plots a column to the screen, and so forth. And it sweeps across this 130 character display, or 130 pixel display, many times per second, 20 some times per second, something like that. So it's actually able to do this quite fast. It responds very well. It's a very quick thing, and it's actually pretty good at capturing transient events. It turns out that even though this is really, in some ways, crude, compared to, say, this, and it's using this type of technique, where I tune to one frequency, take a measurement, tune to the next, take a measurement. I'm tuning very fast. So this sort of gets compressed vertically, and I'm sweeping across very, very quickly, and there's less time for transient events to get lost between the sweeps. So for a while I had this, I always have one in my bag or whatever, and for a while I had a piece of testing on my bench that was like this $40,000 oscilloscope / spectrum analyzer combo, and I was trying to pick up some packets that were very short from some digital radio system, and I was having trouble catching them with my $40,000 test gear. And I pulled out my IME, turned it on. Oh, there it is. Like the IME was able to catch these transient events much better than the $40,000 scope and spectrum analyzer. So because of this one thing, it's cheap. It doesn't have a very wide operating frequency range. It's only it's crude in some ways, but it does one thing very well, and that's tune quickly and move on to the next frequency. So we can do the same types of things actually with all kinds of radio systems that are either digital radio systems or digitally controlled radio systems. And the first thing I want to show you that is a tool that can do this sort of digital sweeping for SDR platforms is a program called Ossmann Spectrum Sense. So in this case, it's not very fast, but it's using this technique of digitally sweeping, or of taking tuning to a frequency, taking a measurement, retuning the radio, and then taking a measurement, then retuning the radio and taking a measurement, and doing this over and over again. And it's designed. It works with all of the different platforms that are supported by GR Osmo SDR, the abstraction layer that supports HackRF and Realtek dongles and various other hardware platforms. I can't remember if I don't have a display of the output here, but it's very similar to the next tool that I'm going to show you, RTL Power. Now this one's specifically designed for just the Realtek dongle, and I don't think it supports any other hardware platform at this time. But it does basically the same thing. It tunes the radio, takes a measurement, tunes the radio, takes a measurement. Now this takes time. Tuning the radio of a device like one of these SDR peripherals takes a lot more time than tuning the radio in the IME. And the main reason for that is that we have to control these things over USB. And there's some USB communication latency every single time we tell the radio to tune. And so it isn't good. This technique is not good at all for capturing transient events. But it's super awesome for sweeping over a very wide range of frequencies and for doing it indefinitely for as long as we want to. So here's an example of the output from RTL Power. Ooh, exciting, right? Yeah. Everybody loves a text file. Sexy. And that's what it gives you. It just gives you, these two tools dump data to standard output. They give you like a timestamp and a little information about how it was tuned, or how the radio was configured, and then the output of a measurement. And that's it. So what do you do with this information? Well, you probably want to visualize it in some way. Maybe you dump these measurements into GNU plot or something. There's a cool tool, and suddenly the name is escaping me. Is it Heatmap? Heatmap.py? Is that all it's called? Yeah, okay, thank you. This is an example of one. Let's see, when was this taken? Is this... Uh-oh. I'm having trouble. Okay, so this is one that I took. The first time I gave this talk was at Hamvention in May, and today I'm giving a slightly extended version of it. But when I went to Hamvention and I was preparing this talk, I ran RTL Power, I think it was, overnight for about 8 hours in my hotel room the night before the talk. And I monitored over the entire range of a Realtek dongle, which is close to 2 gigahertz. So this is 2 gigahertz wide. And it is, that's the width in hertz, and that's also the horizontal scale of this plot. And it's about 8 hours tall. Now, can you see the moment in time when I stopped working on my slides and I turned my phone into airplane mode and went to bed? Suddenly things got a lot quieter through all this section over here. Characteristics changed, and I think the receiver became more sensitive at that time to some things that were at higher frequencies, which is kind of interesting. But there was a lot of kind of wideband noise because I had this close range, relatively high-powered device in my pocket or something while I was working, and then I didn't want anything to interrupt me while I was catching a few hours sleep, so I turned it into airplane mode, went to bed, woke up in the morning, and found this plot. Now, if we zoom in a little bit, you can see that this is extremely rich in information. This right here, I'm zooming in around 1 gigahertz, so you can see a lot of stuff in the upper 800s. That's a lot of cellular bands. You can see stuff. The lower 900s are pretty quiet, which is but there's a little bit of activity in that 900 megahertz ISM band, and then like the first really bright little blips in the that first kind of big bright vertical line north of 900 megahertz is probably pagers around 930 megahertz. Pagers are still around, and they have pretty powerful signals. And so you can see all kinds of different things, and you can see how the spectrum is utilized over time. Now, this was just like with a stupid little telescopic antenna, nothing special, not tuned particularly well for most of this frequency range. But even with that, I find this to be an extremely valuable tool, and you get this very rich data set out of it. All I did was turn on a script when I went to bed, wake up, dump the output into a little program that created this graphic. So here's probably an even better one, and this is a similar one that was done, I think, with a better antenna by somebody who posted it online. I think Tolan was the name of the person, and actually annotated it. So, like, I'm having trouble navigating, but you can see that this has actually been navigating. There's like, this has been notated. So you can actually see, like, on the right-hand side, kind of the most interesting vertical band of blips is decked phones, not far from the right-hand side. There's some mobile phone bands, and then decked phones kind of right in the middle there. Decked is the protocol that's used for home wireless phones, right? Not your mobile phones, but your home cordless phones. Decked is DECT is the protocol that's used for pretty much all those things. There's a little gap in the middle of no information because that particular tuner on the Realtek dongle that was in use has a tuning gap and isn't capable of measuring those frequencies. There's a bunch of mobile phone bands. That's most of the bright stuff you see just to the left of that gap. And you can see some like public safety radio systems and amateur radio stuff. All sorts of cool stuff. So like here you can see, zooming in a little bit, you can see like LTE and GSM, and really get a good idea using this super easy to use tool and super low cost platform. You can do this aggressive spectrum monitoring. Now, all of this is, and here's something that I actually don't know a whole lot about, but I found it online and I was like, wow, people ought to know about this, I guess. It's this program that's a spectrum analyzer software for SDR hardware. And again, it's sort of the idea of, let's take these low-cost hardware platforms that we have and try to reproduce, maybe not reproduce, but try to build new software for them that takes advantages of their capabilities and lets people take measurements maybe in ways that they hadn't thought of using tools other than high-end RF test equipment like spectrum analyzers. And you can actually use an SDR platform as a spectrum analyzer. You can think of SDR platforms, and I often do, as low-cost RF test equipment. Effectively, that's what it is. We have low-cost, uncalibrated signal analyzer and signal generator right here. And we should be able to do a lot of the same things that people have historically used very high-cost tools to do. So, looking a little bit closer at the digital sweeping. Let's assume that we're digitally sweeping a something like a hack RF. That means we're tuning it to a certain frequency, taking a measurement, then tuning it to another frequency, taking a measurement, and so forth. Over time, we tune to different frequencies, and each time, in our time versus frequency plot, which is what we're kind of similar to what we're looking at in a waterfall display, we only get a finite sort of rectangle of information. And the horizontal width of that rectangle, or the bandwidth of that rectangle, is a function of the instantaneous bandwidth of the SDR platform. Now, the instantaneous bandwidth is equal to its sample rate, normally. So, in the case of hack RF, that little rectangle is at a maximum 20 megahertz wide. You get 20 megahertz window, which is about 10 times what you get with a Realtek dongle. Around a 2 megahertz window at maximum. Depending on your sample rate that your SDR platform supports, that's what limits the width of that rectangle, that window, the width of that window. Now, the height of that window is a function of how long you remain tuned to that frequency. And that's both of those things, to some extent, are your choice. But there's some maximum limit to what your sample rate is or what your instantaneous bandwidth is. And then there's some gap in time between when you stop measuring it in one window and then you tune to the next window. And that is the tuning time, how long it takes you to reconfigure the radio for a new frequency. If the tuning time is very long, then we're missing a lot of information that we could otherwise gather if we were able to tune faster. So tools like RTL Power and Osmocom Spectrum Sense are pretty neat, and they let us get very wide bandwidth over a very long period of time. But we may also be able to improve our ability to resolve or measure transient events if we're able to reduce that tuning time. So we have the instantaneous bandwidth, we have the capture time, and we have the tuning time. And those are the three things that affect like what percentage of this big grid is covered by measurement. Question? Oh, good question. Yeah, these things are so low cost, why not use a whole bunch of them? That's a good idea, and I think, now, I can't remember for sure, but I think one or more of those tools, like RTL Power, might out of the box have some support for dealing with multiple dongles. And even if they don't, that's not hard to script, right? If you have like one device monitoring this 100 megahertz chunk and another device monitoring this 100 megahertz chunk, you can do that. Did you have a question? Sorry? Excellent point. You could run into problems with calibration in that case. Like all of these things have little clocks in them, and they all you can't really trust any clock ever, right? Like you know the old thing about a man with two watches is never sure what time it is, but the guy with one knows exactly what time it is. And that's the case in all digital electronics. Like everything has a clock, and some of them are closer to being right than others. It's really hard to take measurements unless they're all synchronized in some way. And that's one thing that HackRF can give you that Realtek dongles can't, is there's a clock input and output, so you can clock synchronize multiple devices. But that's only part of the calibration problem. There's also, having synchronized clocks means that their frequency measurements will all agree with each other. Or their frequency configurations will all agree with each other very, very precisely. But there's also the problem of their power measurements. Calibrating the power level is something that is another problem that you probably have to actually go through some active step to calibrate your equipment and see like, oh, this one picks things up at this frequency 1 dB hotter than this other device does, and so you have to like come up with some calibration measurements and use that to normalize your data in some way. So you have to deal with calibration of both power levels and time and frequency. So those are excellent points. And that's a good suggestion. You can mitigate these problems a little bit by having some redundancy, by like overlapping the windows from one device with another device. Or even if you're using one device, you might actually overlap the frequency windows instead of having one start exactly where the other one ends. There's a lot of opportunity there. There's also some opportunity for like massively parallelizing this kind of thing, right? If you've seen the SatNogs project, super awesome project that's working on building low-cost satellite ground stations with open-source hardware and low-cost SDR platforms. And they're building a distributed network of these things around the globe. But that project has the potential to grow into more than just satellite ground stations. It's a distributed array of software-defined, a global distributed array of software-defined radios. So in the long run, it might be super cool to use the SatNOGS network to do like global spectrum monitoring or astronomical observations. Now, the problems of calibration and clock synchronization and that sort of thing become greater, but I would say that's a good problem to have if we have massively parallel sources of data. Now, one of the things I've been looking at lately is I know that I can choose any capture time that I want, and I know that I can choose any instantaneous bandwidth I want up to the limit of the hardware platform. But what about the tuning time? Can I improve the tuning time? For the most part, that's kind of a fixed thing. Like if you're using a Realtek dongle, you can't change that a whole lot. But what if you're using an open source hardware platform like HackRF, and you could actually run code on the microcontroller instead of running code on the host computer and control and having to do USB transactions every time you want to change the frequency? Aha! And if you want to know more about writing code for the microcontroller, specifically for software-defined radio, definitely come to Jared's talk this afternoon, because he's going to talk about all the code he wrote for the PortaPack, which is running on the HackRF's microcontroller, and all the amazing digital signal processing he's able to do in a very constrained CPU. But I've been experimenting a little bit, and I don't have any amazing results to show you, but I can say that the tuning time that I'm getting, like out of the box with HackRF, without having really optimized time in any way, if I do it on the microcontroller instead of over USB, I get a tuning time of about a maximum tuning time, worst case tuning time of about 750 microseconds, which is considerably less than I can get over USB. With some optimization, and my best case, I think, is about 150 microseconds. So in certain frequency bands, I really can tune super fast and reduce a lot of that transient time, that time during which I can miss transients. And if I can reduce that tuning time to a bare minimum, then this grid becomes more and more full of pink rectangles, right? We get a higher duty cycle, a higher percentage of the available information is getting captured. So this is something that I think we should be doing more of, and it's something that I think would be good to work on for the PortaPack too, which Jared will talk about this afternoon. So I'm using the microcontroller in the HackRF, and there are other software-defined radio platforms where we should be able to do this too. Any SDR platform where you have control of the tuning from the device itself, from the embedded device itself, as opposed to control interface like USB. Generally speaking, I think HackRF's the lowest cost device, at least it's the lowest cost transceiver that gives us that capability. Unfortunately, the Realtek dongles, I don't think, have a way to give us that capability, although it would be cool if somebody figured out a way to hack that in. But so to give you an idea of how much we can fill that grid with those rectangles, the instantaneous bandwidth of HackRF1 is about 20 megahertz. So that means every rectangle is wider. And with an RTL SDR, we can get about 2.5 megahertz. The hops per second with a Realtek dongle. Now, when I was trying RTL power and stuff, I seemed to only get, I don't know, maybe about 10 hops per second, something like that. But I've heard accounts that people with some tweaking of the software can get something around 40 hops per second. So that's 40 retunings per second, which is definitely useful, but it's way, way, way less than we can get by running on the microcontroller in HackRF. So at 750 microseconds of tuning time, I can very easily achieve upwards of 1,000 hops per second. And that means that we have much greater capability to make this observation. If you think of this two-dimensional, this imaginary perfect waterfall plot in the sky that has frequency on one axis and time on another axis, and you think, how much of that big plot are we really measuring? Well, by tuning much, much faster, we should be able to fill that in and measure a lot more. Come visit me at GreatSkyGadgets.com if you're interested in this stuff. I definitely recommend checking out the SDR video series that I've been working on. It's an outgrowth of the in-person training that I wrecked my voice doing the last 4 days, and I'm adding more videos from time to time. So if this stuff intrigues you and you are new to SDR, I hope you'll check out the software-defined radio video series there. Are there any other questions or comments? We had some really good ones so far.
When you eliminate USB as the great limiting factor, what are you running into that's limiting USB?
Yeah. The question is, if we eliminate USB from the tuning time, what is the limiting factor? Why does it take any time at all to tune? And yes, it is primarily the PLL lock time of the frequency synthesizer that is producing the signal. Now, in the case of the HackRF, it's complicated by the fact that we have a dual conversion architecture, and so we have two different mixers to tune. In some cases, we might be able to just not tune one of them, leave it fixed, and only tune the other one, and save a whole lot of time. So there's the time that it takes for it to come into lock, and then there's also the time that it takes to configure it. We have some kind of a serial interface between the microcontroller and the synthesizer chip, and we have to, it takes some finite amount of time to actually give it a command. Just like it takes a finite amount of time to give a command over USB, but it's much less than the time it takes to give a command over USB. So those are kind of the two limiting factors, is the serial interfaces to control those synthesizers and the lock time that it takes for them to lock into a new frequency. Other questions? Yes?
When you're doing the very wide scans, how much does having just a single antenna hurt performance at the ends? Have you looked at doing multiple antennas and switching between them or anything like that, or does it just not make a big difference?
Does it not make a big difference to have just a single antenna as opposed to multiple antennas? I would say it really depends a lot on the very particulars of your application. There are some antennas that antenna designs that are very wide band, like that measurement that I took in a hotel room. I would have been much better off using a disc cone than I would using a telescopic antenna, but the difference is a disc cone doesn't fit in my backpack. So that's not what I had at the time. There are horn antennas and various designs that are specifically designed to give you a good response over a very wide frequency range. And but generally speaking, any antenna only has good performance over a limited frequency range, and every antenna is different. So if you can kind of have a set of antennas that are all used effective, like if you're doing the array kind of stuff, array of multiple receivers, and each one has its own antenna that's better for that particular frequency band, you might get much better performance. Also things to consider, like the polarization of the signal. Is it horizontally, vertically, circularly polarized? What direction is the signal coming from? There are all kinds of measurements we can make beyond just the stuff that I've been talking about. If we want to monitor spectrum on a large scale and observe how it's used, like it might be nice to know where the signals are in addition to what they are as detected from a given point. So all those things can be accomplished theoretically with multi-antenna techniques, either by switching between antennas one at a time or by using many antennas simultaneously. One more. A little program called Heat Map to create those images out of the RTL power output. Okay, two more.
With RTL power, have you ever done anything to characterize one of those, like just hook up a dummy load, do a scan, and then use that to subtract from a live scan?
I have not done that. Question is, oh, and thank you for loaning me your Realtek dongle. The question is, have I tried to characterize the output that I get from RTL power by putting a dummy load on a device, maybe throwing in a Faraday cage or something like that, and taking measurements so I get some sort of a baseline of what this device gives me, even without any radio signals present. I haven't done that personally. It's a good idea to do that, and that ties in with some of the comments earlier about calibration, that could be an excellent way. I think that if you play with RTL Power a little bit, or Osmocom Spectrum Sense, or GR Phosphor, or some of these tools that I talked about today, I think you'll find that you're able to explore stuff that you weren't able to explore before. And I encourage you to start playing around, see what you can see, because before you get too hung up on calibration and is my measurement perfect, it's so cool just to have the ability to visualize these things and make observations. One of my goals, in making HackRF, for example, is to give people uncalibrated test equipment, because yeah, you can go through the effort and calibrate it later, but you shouldn't have to pay for all that calibration now. It should be more accessible for people to start exploring and look around and see what you can find around you. I hope you have a good time with it. Thanks very much.